My talk is about we're a group of researchers belonging to a project called SACIA, two projects, SACIA and its follow-on SACIA-2, signatures of aerosol-cloud interaction over the Arctic, and basically it's about remote sensing of aerosol-cloud interaction, supported by collaborators, other members of the team making surface measurements and modeling. And people come from University of Sherbrooke, University of Quebec à Montréal, Dalhousie University, and University of Montréal. And we all belong to a group called CANDAC, which is the Canadian Network for Detection of Atmospheric Change. I want to go over five points today and talk about the surface measurements. And what I wanted to say was we're interested in the whole Arctic, but we're focused on our observatory at Eureka called Pearl. So I'll talk about the surface measurements made at Eureka, satellite and ground-based examples of remote sensing of aerosols over the whole Arctic and Eureka. Illustrations are always illustrated in specific events showing aerosol cloud interactions. AC is my acronym for aerosol cloud. Then aerosol cloud analysis in the context of indirect aerosol effects and the influence of Arctic scale intrusions on warm water vapor and the creation of polar stratospheric clouds. Surface measurements at Eureka. We have Patrick Hayes at the University of Montreal and Rachel Chang at Dalhousie have maintained measurements at Eureka for over 5 years now, if I got my numbers correct. And here's one example of optical measurements of absorption coefficient and scattering coefficient at the Ridge Lab, which is 610 meters above sea level at Eureka. 2 wavelengths, and this type of information, scattering and absorption, is obtained with an extinctiometer, and it gives you can retrieve a refractive index, real and complex, and do things like speciate aerosols, help to speciate the type of aerosols. So here's one example of the measurements at Eureka. I wish I had a pointer, but up above is aerosol mass spectrometer. It's a mass concentration as a function of time for about a week, and it's speciated into organics, sulfates, nitrates, and ammonium types of aerosols. And then on the bottom is measurements made at Eureka with using an SMPS, a device that measures the particle size distribution of the submicron aerosols. And on the y-axis is the diameter of the aerosols, and time is on the x-axis, and the colors indicate the strength of the particle size distribution. So most of the particles were around 50 nanometers diameter, so about 0.025 micrometers radius, and what it tells us is that where the PSD is at its strongest is due to organics. If you can keep that in mind for, this is during the summer of 2015. Just keep that in mind for a later slide. Satellite and ground-based aerosol remote sensing measurements. This is work by my ex-PhD student, or my former PhD student, K1 Ranjbar. And on the left is a MODIS image over our Pearl site, and the red and the blue, red and the green spots are. We have 3 labs actually, but 2 labs that we use to make measurements at Opal at sea level, and the Ridge Lab at 610 meters altitude. And on the right, the top plot is a function of time. We have 2 AeroNet CMLs there, and this shows the plot, the optical depth, the fine mode, submicron optical depth of those 2 CMLs. And it was during an extreme event that occurred in Prince Albert, BC, and made its way to Eureka. And we proved with using extreme statistics that this was the greatest optical depth ever measured at Eureka. And the reason there's two graphs and they're displaced. Why are they displaced? Because the time it took to get between those two sites there. And another event that K1 Ranjabhar found, there was 300 kilometers to the northeast of Eureka. How am I doing? Okay. Oh, good. Okay. 300 kilometers northeast of Eureka is something called Lake Hazen. It's the greatest natural, by volume, the largest natural lake in the Arctic. It's also called an oasis in the summertime. And what we see is during the winter shot there is a plume of dust coming off its drainage basin of a glacial river flowing into Lake Hazen. And we see the plume very well. The image is taken by MODIS. And below is a zoom of that MODIS image where you can better look at the plume. And on the right is an infrared image where we're looking at something called a brightness temperature difference. It's kind of a signature of dust, and it proved that the blue proved it was dust. Or the cold temperature proved it was dust. And then on top is another retrievals of another sensor. It's the y-axis is altitude. The x-axis is distance. And the green line is the surface of Lake Hazen area, and the dots are using stereoscopic techniques. The height of the plume obtained by the Miser multi-angle imager. And on the bottom is LiDAR, Calliope LiDAR on the A train. And the brightness of the points and the different colors are indicative of the strength of the backscatter of the aerosols, and they more or less coincide to the positions of the plume heights in the upper plot. Here, this is an event that we're very interested in over Barrow. There's a lot going on in there, but where we see these ellipses here. We believe that that's Asian dust, and the back trajectories kind of confirm it. That's Asian dust, and what's interesting, just one second, at the bottom left is a particle size distribution retrieved using the AeroNet instrument at Barrow. On the right of that is a variation of the optical depth. There's smoke in that image. We don't want to know about smoke. We want to know about the bottom optical depth, which is very weak, and it's supermicron optical depth, and that's typical of Asian dust plumes. And the back trajectories indicate it probably is Asian dust plumes. And what we were very interested in is that the variation of the larger peak there you see on the left is about 1.3 micrometers of radius, corresponded very well with the variation of the optical depth. And it agrees with a climatology that one of my students did over Barrow. It showed a similar peak varying with the Asian dust, which I didn't say arrives in the spring. More at Eureka. This is fine mode aerosol optical depth measured at the Ridge Lab versus the concentration of fine mode aerosols measured by the surface device, the SMPS. All kinds of different variations there, the kind of signatures of different kinds of aerosols. And the one that rises rapidly is what you see there is the variation of the fine mode aerosol optical depth on top, and then below that are profiles. The rightmost one is the Kandak Raman LiDAR. It shows a plume at about a smoke plume at about 5 kilometers altitude, and that means that the CMEL, the AeroNet device, sees that very well, but the SMPS at the surface hardly registers it, so you get this very large slope. Whereas for a boundary layer event, there's lots of variation of the surface concentration, surface mass concentration of the SMPS, but it's right at the limit of the sensitivity of the CMEL instrument, and the curve appears flat. The points appear flat. Event level remote sensing of aerosol cloud interactions. This is southern Alaska and the Gulf of Alaska, and what you see there streaming off the land are drainage basin, river basin erosion of dust, and it looks like it's forming cloud particles halfway over the Gulf. And that same image, that was a MODIS image, that same image, there are products associated with that. And here we see on the left is something varies with the concentration, the columnar concentration of aerosols, the fraction of submicron aerosols, and on the right is the cloud optical depth and the cloud effective radius. And with that, well, all that, we can put a picture together of the interaction between the aerosols and the clouds, and understand the physics better. This is the same for the same scene. My image is the red rectangle up there, and that solid red line is the Cali-up LiDAR going across that rectangle. And what we see is that's the backscatter profile, the strength of the backscatter, and the second image is the depolarization ratio. And when it's blue, it's low depolarization. It's associated with the aerosols. When it's large, it's the clouds. And we think that we can see the plume going right across the Gulf there, and that we can see, at least at the complete left side of it, a form of nucleation into the lower level clouds. Analysis and, oh, you're going to cut me off like that? No. Eureka, the measurements, in black, you see some measurements of particle size distribution measured with the SMPS again, and observations, and then we ran a model trying to predict this particle size distribution, and it totally failed. But you remember the secondary organic aerosol plot that I showed before. When you add secondary organic aerosols to the model, then they agree a lot better with the observations, and it leads one to conclude when you put things together that it's secondary organic aerosols. And where do they come from? The marine aerosols. Secondary organic aerosols from marine sources. And this just says that the fraction, the modeled fraction is a large fraction. So what happens, those secondary organic aerosols added, the backscatter of those secondary organic aerosols is what we call the first effect. Sorry, the direct effect of aerosols, and the backscatter is very weak. So the rate of forcing associated with that is not large, but the rightmost circular plot, those aerosols induce change the properties of the cloud. They change the cloud albedo, and the rate forcing effect of those particular aerosols, secondary organic aerosols, was much more important. 10 times the direct effect. I think I'll have to skip that, I guess. This is profiles of the top graph. CRCMC 6 is the Canadian Regional Climate Model 6, version 6. The simulations of ice water content, ice water content of crystals, and the plot, the second topmost plot are actual measurements of ice water content made by the CloudSat radar on board the airtrain with Eclipso. And below that, the two below that are effective radius of the crystals measured by the model, or sorry, predicted by the model, and measured, retrieved by the the tandem of the two sensors, and what we find is they generally agree, and not too badly, but the model tends to underestimate ice water content and the effective radius of the crystals. So I'm nearly done. So this, I want to talk about, this is Liviu Ivanescu's work. This is a Calliope profile, basically over Eureka. The red line in the map in the top right there is the orbit of Calliope. And what it shows, first of all, is the backscatter, all those colors, the backscatter intensity of the backscatter. What has been superimposed on them are the different cells, polar dome, the circulation cells. The polar dome, the most important one, polar cell. Then the ferrule cells on the right and left, and these cells tend to control all this, in general, all the circulation that goes on over the Arctic. And what it shows is an intrusion of warm, wet air. This is basically an atmospheric river intruding over into the stratosphere and inciting polar stratospheric clouds, which in turn incite an ozone hole during certain years over the Arctic, and even descend in the troposphere and become water vapor clouds. I think I better, I'm sorry, taking too much time. I know I don't have any time for questions.